scale height increases, showing that contrary to what we thought, the scale height increases when the moon is in the Earth's magnetosphere, and the density would result in a different scale height. The scale height, of course, for PSA would be the least, and scale height for sputtering would be greatest. And so these were the runs, turning the polar cold trap on and off, the re-emitted fraction. Normalization between 20%, 50%, and 100%, and then computing the dawn to dusk ratio, pole to dusk ratio, and subsolar to dusk ratio for each of these runs. And so what you see then is the re-emitted fraction really influences the pole to dusk and the dawn to dusk, and that's because what you're looking at is if are re-emitted when that particular portion of surface comes back into sunlight, and if it's 100% re-emitted, then you'll get a really large dawn enhancement, and if you assume 25% are re-emitted, then you get much less of a downside enhancement. And so then you look at the polar cold trap. It affects the dawn to dusk ratio much less. And so we compare this with the data, and what it looks like is that we do need the best results are if we do have a polar cold trap. If the re-emitted fraction is probably about 25%, because we don't have a really large dawn-dusk asymmetry. We do see that at the moon, the sodium is thermalized. This is interesting to me because when I look at the sodium atmosphere of Mercury, it doesn't look like the atom's thermalized. So this is kind of curious. This is some work that Menelaus did, and this is the portion of this graph to the left of the dotted line is when the moon is inside the Earth's magnetosphere. And you can see that the upper, the dashed black line is the model for photon-stimulated desorption. And it fits pretty well with the data that are outside of the magnetosphere. But you can see that the data when the moon is inside the Earth's magnetosphere are all less dense than you would predict for a normal PSD, either if you assume that it falls off as cosine of the solar zenith angle or cosine squared. So something is influencing the efficiency of photon-stimulated desorption, and we think that this is something that we call ion-enhanced PSD. In other words, when the solar wind impinges on the surface, it acts to prime the surface so that photon-stimulated desorption is more efficient. This is some Kaguya data, and you see the exact same trend. You see a less dense exosphere when the moon is inside the Earth's magnetosphere than when it's outside. So in conclusion, the sodium observations in 1998 and also the Kaguya and other data show that there's a range of density and scale height, and it varies not only with position around the moon, but it varies with solar, the position of the moon, the phase, and in particular when the moon is inside the Earth's magnetosphere. You get lower density, but you also get greater scale height. And so why do you see a greater scale height when the moon is inside the Earth's magnetosphere? When the moon is not exposed to the solar wind, you would not get sputtering, ion sputtering from solar wind. So why is the scale height larger? Well, you still have impact vaporization. So if you have a constant impact vaporization source, which you probably don't, but assume that you do, then that source would be more dominant when the PSD source declines. That's one possible explanation. You also, if the moon goes through the plasma sheet, then you would get sputtering, and sputtering from heavy ions, which are in the plasma sheet, is more efficient than sputtering from the protons in the solar wind. So that's about it. Thank you.
I have a question. Did you and Dana turn the radiation pressure on for these runs? Radiation pressure, was it on during these runs?
I'm not sure. Dana, did you turn radiation pressure on? It's on? Okay.
Any other questions? John?
How does the brightness of the sodium emission compare to like what over the horizon dust? Is there a comparison you can make in terms of brightness?
Well, actually, yeah, we actually looked where you get scattering by the dust. You can't see the sodium in that signal, so it is it's brighter. But that's one reason why we look at very high resolution images, because if you just looked with a broadband, if you just had a filter, you wouldn't see the sodium emission. You need a really narrow, that's why we're using a shell spectrograph, because the emission is very, very narrow, and you want to exclude the light from the continuum is much brighter.
Great, right on time. And next, Jasper Halicus will talk to us about lunar pickup ion